Today's video is all about mass and energy, and it continues with the particles topic, and we're really getting into the advanced physics level here and taking ideas from lots of different areas. And first person I would like you to meet is this gentleman called Paul Dirac. In 1928, Paul Dirac proposed, based upon equations that he'd come across or he'd developed, he discovered that there were two solutions to his equations. And he proposed that the form of matter that we're familiar with was not the only form of matter, that there was a second form of matter which he called antimatter. He won the 1933 Nobel Prize for his discovery of antimatter, and there's a great book by a guy called Graham Formello detailing both the life and work of Paul Dirac, which I would greatly recommend to you. It's quite a light read, so once your exams are done in the summer holidays, you might be interested in delving into the life of this extraordinary genius. Anyway, Paul Dirac proposed this existence of antimatter. This is a detector photograph taken in 1932, so 4 years after Dirac's proposal, by a fellow called Carl Anderson, who in turn won the Nobel Prize in 1936 for this. And at first glance, this looks like a very familiar track to us. And if you haven't seen my video on detectors and tracks, I will put a link to it here. We can see that the particle that made this track is coming in from the right-hand side here. And we know this because the radius of the track is decreasing as it goes along. And we know that that happens because the particle loses energy as it ionizes. It's a very thin track, which means the particle is very small and very light. And so we might say to ourselves, this is an electron, and it is moving from right to left through a magnetic field. However, the magnetic field here is into the screen. So if you use Fleming's left-hand rule, and take a moment to do that, point your first finger into the screen. Your second finger runs along the direction of the current. Now remember, direction of the current would be opposite to the direction that an electron is moving in. You will see that the force that is exerted should be in this direction, which means if this were an electron, it should be curling in the opposite direction. The reason this photograph is so famous is because this is the first detection of antimatter. What Carl Anderson actually detected was the antimatter particle of an electron, and this was called a positron. There are various different nomenclature for positrons. Sometimes it's given P with a little plus, sometimes it's given, more commonly now, E with a little plus so it doesn't get confused with a proton. And of course, because it is effectively an electron, it has the same mass as an electron, it just has the opposite charge. And that is true of all antimatter particles. So the proposal is that all matter has an equivalent antimatter particle. And for example, a proton, an antiproton would have the same mass as a proton, but instead of having a positive charge, it would have a negative charge. And we'll come back later to all the different kinds of particles in the next video and their antimatter equivalents, but their masses are the same, their charges are opposite. This connects in with today's video because essentially today's video is all about Einstein's very famous equation, which proposes the exchange rate between mass and energy, and that exchange rate is 9 times 10 to the 16, or the speed of light squared. And it tells us the equivalence between the two, that mass can be transformed into energy, and in turn, energy can be transformed into mass. And this is what we find with antimatter in particular. When a particle meets its antiparticle, they undergo what is called annihilation. What that means is that an electron and a positron, for example, their mass turns into pure energy and they become a photon. The opposite can also happen, and that's known as pair production, in that energy in the form of electromagnetic radiation can be turned into mass. So a photon of electromagnetic radiation can produce an electron and a positron. This photograph here is showing us pair production. Ignore this green line over on the left-hand side, and we're focusing on here. The photon is coming in along here, and of course you don't see it because it's not a particle and it's not charged, so it doesn't show up at the detector. At this point here, that photon turns into a positron and an electron, and you can see that they're opposite charges because they're going in opposite directions in this magnetic field. But their tracks are of a similar size, so their speeds, their masses, they're the same. And we can do a calculation, and we should be able to do a calculation on both annihilation and pair production. So this is a calculation on pair production. Show that the minimum gamma ray energy, so those photons are always gamma rays, because the amount of energy that you need to produce mass, remember our exchange rate, is a lot. And so they end up being gamma ray photons that produce mass. So in order to produce an electron-positron pair, always in pairs, show that the minimum energy needed is 1.2 mega electron volts. Okay, so the mass of an electron is given in our data. It's something that we should be familiar with, 9.11 times 10 to the minus 31 kilograms. So if we're going to produce an electron-positron pair, then we will need to multiply that by 2 because that's the amount of mass that we're going to produce, giving us, obviously, 18.22 times 10 to the minus 31 kilograms. So how much energy then is that equivalent to? We use Einstein's equation to find that, and we're substituting our 18.22 times 10 to the minus 31 in for delta M here. And that gives us an energy of 1.6398 times 10 to the minus 13 joules. Now obviously we know that joules is one unit of energy, electron volts is another. We're going for mega electron volts here. And we'll do it the slow version, 1.6 times 10 to the minus 19. We'll convert it into electron volts, but 1.6 times 10 to the minus 13 will convert it into mega electron volts, because obviously there's a power of 6 difference between those. And when you divide that by 1.6 times 10 to the minus 13, we get 1.025 mega electron volts as required. Now let's look a little harder at the world's favorite and most famous equation. This picture here is showing an iron nucleus coming in from space on the left-hand side. It strikes an atom of silver in the photographic emulsion, and what you get is the shower of particles being produced. The kinetic energy of that incoming iron nucleus is turned into all of these particles that we see. All of these tracks represent particles produced by the smashing of this iron into the silver. In other words, mass is being produced from energy. A lot of people think this equation is only about nuclear power. The mass defect gives us energy, but the opposite is also true. We get to produce these particles if we have enough energy. Remember, again, 9 times 10 to the 16 is our conversion factor, so in order to get a tiny bit of mass, we need to have an enormous amount of energy. In my accelerators video, I talked about a cyclotron and that we accelerated electrons or particles in a cyclotron up to 10 mega electron volts. So let's look for a moment at what speed you would get an electron to if you accelerated it to 10 mega electron volts of kinetic energy. So 10 mega electron volts is 10 times 1.6 times 10 to the minus 13 joules. Remember, it's mega electron volts, so it's minus 13. And that is going to be equal to half mv squared. We know the mass of an electron, 9.11 times 10 to the minus 31. So if we find a value for v here, we should get our velocity of an electron as 1.87 times 10 to the 9 meters per second. Now, of course, immediately you should see there's a problem with that, because that is greater than c, the speed of light, and that is impossible. So what is going on here? Well, we have to stop thinking of mass and energy being different things. When you accelerate an electron, you give it kinetic energy. But that kinetic energy is effectively mass. And we call the rest mass, the mass of an object that is not moving, its rest mass, m0. When we accelerate it and we give it kinetic energy, we add on the equivalent mass of that energy onto the particle. So the particle gains mass by gaining energy. Now, we don't notice this at human-like speeds. You don't notice yourself gaining mass when you go for a run. But it becomes very, very significant when we get to close to the speed of light. And the difference in mass, the change in mass, the new mass, when you add on the delta M, is significant compared to the rest mass of the particle. So again, in my accelerators video, I referenced the Stanford LINAC accelerator, and those get energies of 50 giga electron volts. And at this point, our rest mass is negligible compared to how much mass you've gained because of this kinetic energy. And this little graph here summarizes it very well. You can see that at speeds that are human-like, are slow, not even close to c, the delta m, the change in mass because of the gain in kinetic energy, is negligible. But when you get up to 92.5% the speed of light, for example, it starts to increase very, very fast, and you get an effective mass of 2.5 times the rest mass. Now, this is what we call relativistic effects, relativistic speeds. And while you don't need to know much about relativistic effects, you need to realize that they are there and recognize them when it's relevant. And here is one of the relevant times you need to know about time dilation. And there's a nice little limerick here written by Ben Buckley that talks about the twin paradox. That is one of relativity's favorite consequences. The idea that if you had two twins born on Earth and one of them left Earth traveling at relativistic speeds, by the time they came back, they would be younger than their twin. That is because particles that move do not have the same time as those that stand still. For a particle that moves, any particle that moves, not just relativistic, but you only notice it with relativistic speeds, any particle that moves, their clocks tick slower. A second to a moving particle is not the same as a second to a stationary particle. Their seconds are longer. And here's a nice example. If we're looking at the decay of a particle, so you're in an accelerator or whatever, you're observing the decay of the particle, and you know that its average lifetime is 1 times 10 to the minus 6 seconds, 1 microsecond. If it's traveling at 90% of speed of light, that's its speed. So using classical physics, distance equals speed times time, we would expect the particle to travel 270 meters and then decay, or thereabouts. It's an average lifetime, so we'd expect sometime very close to 270 meters, we'd see this particle decaying. The problem is, it's traveling at 90% the speed of light, so it's going to defy our expectations. Its seconds are longer than your seconds. And there is a time dilation factor. It's not on our specification, unfortunately, but you can actually calculate how much slower or how much longer their seconds would last using this fairly simple equation. So your time dilation factor is given this symbol gamma, and you put in your v into where you see the v squared at the bottom there. And that will give you the factor by which your time is increased. And if we do that for a particle traveling at 90% the speed of light, we'll find our time dilation factor is 2.29. That means that instead of having a lifetime of 1 times 10 to the minus 6 seconds, we have a lifetime of 2.29 times 10 to the minus 6. And we'd have to redo our calculation. When we do that, same calculation, distance equals speed times time, we'll find that actually instead of 270 meters, which was our original calculation, that particle is going to travel 619 meters before it decays. If you're expecting to catch its decay with a detector, so you put your detector at 270 meters, you're going to be disappointed, because it's not going to decay there. In fact, it's going to decay somewhere around 620. This is in our specification. It's not very often asked because it's difficult to find a situation in which you could ask this, but in 2019 they did ask. The muons are produced, there was an earlier part of the question about muons, at a height of 10 kilometers in the atmosphere. The velocity of them is 0.99 c, so 99% the speed of light. That's their average lifetime, normally 2.2 microseconds, and yet you find them at sea level. So they're asking you to explain what is going on here. So if you think about this, okay, 99% the speed of light is 0.99 times 3 times 10 to the 8, which is 2.97 times 10 to the 8 meters per second. That is the speed that our muons are traveling at. If they have a lifetime of 2.2 seconds, then we can say, okay, same as we did above, distance is equal to speed times time. We should get a distance of 653.4 meters. Now that is how far those muons should travel before they decay. The problem is, of course, we can detect them at sea level, so we know that they're not only traveling 653 meters. And the reason for this is because relativistic effects come into play. Because our particle is traveling close to the speed of light. So their lifetime is going to be much longer than 2.2 times 10 to the 6. And this is literally what they're expecting you to say. And in fact, we can figure out what their lifetime is and what their time dilation factor is, because we know that if you're going to travel 10,000 meters, which is what 10 kilometers is, at 99% the speed of light. Time is distance over speed. That'll be 10,000 divided by our 2.97 times 10 to the 8, and we get 3.37 times 10 to the minus 5 seconds. So that is their new lifetime to us. Now remember, to the particles, that's still 2.2 microseconds. If they were counting it, they would still think it was 2.2 microseconds. But because we're stationary relative to them, to us it looks like 3.37 times 10 to the minus 5. And if you compare then their 2.2 seconds with 3.37, you'll find that it's a factor of 15. So their time dilation factor is 15. They are lasting 15 times longer than we expected. There is one more thing you need to be able to do with this equation. And it's a thing that is always asked, because students get very confused about it. We know, and we discussed before, that the unit of energy traditionally is joules, but for particles we use electron volts, we use megaelectron volts, we use gigaelectron volts. You cannot use these units in our famous equation. If you're going to put numbers into that equation, that energy has to be in joules. But you get particle physicists all the time just talking about the energy of particles in electron volts, megaelectron volts, gigaelectron volts. Obviously they know it must be converted into joules, but it's much more convenient to use it in electron volts. You also hear particle physicists and read them in papers talking about the mass of an electron or mass of a particle in megaelectron volts and gigaelectron volts. Because to them, mass and energy are interchangeable. What they mean is the mass that would have an energy of 10 megaelectron volts. So they'll talk about the particle has an energy of 10 megaelectron volts, the particle has a mass of 10 megaelectron volts, because to them, they're just automatically using the equation. Now strictly, let's just use 10 megaelectron volts as an example. You can call the energy of a particle 10 megaelectron volts. If you're going to use the mass equivalent, you should be calling the mass of the particle 10 megaelectron volts per c squared. But that's just so awkward that people don't use it a lot in the real physics world. When they say that it has a mass of 10 megaelectron volts, they mean if you turned 10 megaelectron volts into joules and then put it into the equation to find the mass, that's the mass you would get. As an example, we won't go with 10 megaelectron volts, we will look at what has actually come up in a past paper before. The mass of the Higgs particle is 2.2 times 10 to the minus 25 kilograms, gives this mass in gigaelectron volts per c squared. What they're really saying to you here is, give us the gigaelectron volts energy equivalent of this mass. What is its energy equivalent? We're going to put it into Einstein's equation, find its joule equivalent, and then turn that into gigaelectron volts. And that we'll be able to say is its mass equivalent. So, put down our equation. Obviously our delta m here is 2.2 times 10 to the minus 25, and our c squared is 9 times 10 to the 16. I rarely write down 3 times 10 to the 8 with a square in it, because what often happens to people is that they write that down and then they forget to square it. So you should always think of c squared as 9 times 10 to the 16. That'll give you an energy in joules of 1.98 times 10 to the minus 8 joules. Now we need to convert that into gigaelectron volts. Giga is 10 to the 9. We know that to convert to 1 electron volt it would be 1.6 times 10 to the minus 19. So we're just going to divide by 1.6 times 10 to the minus 10, because that's going to be the gigaelectron volts equivalent, and we get 123.75 gigaelectron volts. So we're saying that 2.2 times 10 to the minus 25 kilograms is that much energy. In other words, this mass in gigaelectron volts per c squared is exactly the same. Those are exchangeable units. It's done for convenience. It's done so you can talk about mass and energy in the same unit and not have to worry about constantly switching from one to the other. You need to be able to do this, both converting kilograms into gigaelectron volts per c squared and converting gigaelectron volts per c squared into kilograms. To do that, you take your 123.75 gigaelectron volts per c squared. How much is that in kilograms? Just let that be 123.75 gigaelectron volts is your energy. Forget about the c-squareds. That's your energy for that equation. And then you put that in, turn it into joules, put that into the equation, you then divide it by c-squareds and it'll come out in kilograms. I will do an example of this in the next video where I'm going to be talking more about matter, and it comes up when we talk about various different particles, and there'll be an example on there.